Okay, so our next speaker is Nick Brody, and he will tell us about groups acting on trees via number theory. So please.
Awesome, thanks for the invitation. Yeah, so I'll be talking about groups acting on trees. So yeah, I mean, I think in a way this is kind of an advertisement of a toolkit, I guess. So we're going to discuss Serre trees, and then discuss some simple coordinates on these trees. I think a lot of people have kind of thought about these, in the more general sense, but don't really know how to get down to it and do computations. And yeah, so we'll discuss some ways that, this Serre's theory gives a bridge between group actions on trees on the one hand and number theory on the other. Okay, so we'll begin from the ancient insight that the general linear group of a vector space acts on the set of ordered bases for that vector space. And yeah, thinking about this like kind of big action, we get a bunch of like other actions that follow, right? So I guess kind of in a way like this is a torsor for the group. And so we can take different like related things to this set and get different actions. So if you act on the ordered bases, you act on bases, you act on the flags in the vector space, you act on the k-dimensional subspaces of the vector space, you act on the projective space or the one-dimensional subspaces. And kind of most relevant to our purposes, if V is defined over a field K and you have some subring R, then GLV acts on the space of R lattices in V. And so the action preserves these homothety classes of lattices, right? So take one lattice, hit it with an element of GLV, a scaled version of this maps to a scaled version of that. So I'm saying it commutes with the center really. And so the center acts trivially on the homothety classes. And since we're looking at R lattices, maybe choosing coordinates, we get an action of PGLN R by changing bases, and this then acts trivially on the R lattice. So, in this special case, taking K to be the p-adic numbers and R the p-adic integers, and taking N2, we get this action. Yeah, so I mean, I won't really define the p-adic numbers, but it'll kind of, I don't know, if you're not super familiar with them, we'll get some visualization of them that might help you. Okay, and so here I want to discuss these coordinates that I find helpful for thinking about this action. So every lattice in QP squared is homothetic to a unique one spanned by vectors of the form p to the n0 and q1, where n is an integer and q is something like this. Okay, so we think of it as an integer where the denominator is just the power of p, and we think about this up to mod p to the n. Okay, and so let's observe this as an infinite, countably infinite set. Okay, and so yeah, how do we do this? Just take any basis for your lattice L, and right, since it's a basis, we can't have C and D both 0, and we may as well take up to ordering these a different way. Let's say that this has a higher power of p dividing it than this one. And so, I mean, what is that? That means that C over D is divisible by p. Or I guess that, it's a p-adic integer really. And so we're allowed to scale by non-zero p-adic numbers, scale the whole lattice. And then we're allowed to modify the bases by doing ZP linear column operations. And so, okay, this here says that is a p-adic integer, and so we can do that ZP linear column operation of subtracting the C over D multiple of this guy from here. And that gives us, AD minus BC over D up here and a 0 down here. And we can scale the whole matrix by D. Well, yeah, divide by D. And we'll get something of this form, in which case, there's kind of like this polar thing for p-adic numbers, which says you're a p to the n times a p-adic unit. And so we'll scale this by a p-adic unit, which is an allowed linear column, ZP linear column operation, and just get it in the form p to the n 0. And then we'll n truncate this, okay? And that's basically just finding an equivalent thing that doesn't have any, order above n. Okay, if you're not familiar with p-adic numbers, that doesn't totally make sense, but we'll see what these actually look like in a moment. Okay, so the local structure of the tree, all I've said so far are this is how you label the set, but now I'm gonna describe these as vertices of a tree. And so, okay, we put our lattice into this form, p to the n q01, where q is in this set. And there's going to be one vertex above it in the tree, which is truncate just a bit earlier. And then there's going to be p below, which correspond to the p different ways to add a multiple of p to the n in this set. Okay, so we have this n plus first level, and this is q plus 0 p to the n, q plus 1 p to the n, q plus p minus 1 p to the n. And so you can see this is a p plus 1 regular graph, I guess. But with these coordinates, it's pretty easy to check it's a tree. Once you check that there's a unique lattice of this form, then you can really easily take two coordinates, what's their distance, you can find nearest point above them, connecting them or something. So let's look a little broader at this tree. So, really what I'd like to do is kind of highlight the analogy of these coordinates with the coordinates of the upper half plane. And so this n piece, right, that is your p to the n, that's like the imaginary part of a point in the upper half plane. And there's kind of this like nice axis here that just consists of p to the n 0, 0, 1 matrices. And so you can go up, 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 and then start going down, or you can go up, forever, and you'll reach sort of, maybe a point at infinity up here. And then let's kind of highlight some relevant things. So I guess I'll mention that the boundary of the tree corresponds to like the projective line over QP. And so here's our infinity up here. And our QP is sort of the real axis of this. It's the bottom. And so that's when, as you go to n, as you send n to infinity, you complete out, this p-adic number. The p-adic integers are exactly the ones you get from starting at the base vertex and moving down. And if you start by going farthest left, this will be the set of p divisible p-adic integers. And like the complement of these here, you can see this set. This is the p-adic unit, ZP cross. Those are the ones with non-zero part reduction into FP. Cool. So, and then given an element of, PGL2Q or QP, you can compute the way that it acts on this tree by multiplying it by the vertex and then reducing it according to above. And yeah, I mean, this is really easy to say implement in Mathematica and just do all sorts of computations. And so let's do a couple computations by hand here. So let's look at this matrix A, 3, 0, 0, 1/3, and see how it acts on the three-adic tree. So the tree corresponding to prime equals 3, which is 4 regular, right? There's, the P sub P tree is going to be P plus 1 regular. I'm indexing by the prime. So if we multiply something along this axis by A, we're going to get 3 to the n plus 1, 0, 0, 3 inverse, 1/3. And then we want to scale this whole matrix by 3 according to that algorithm we described before. And you're going to get 3 to the n plus 2. And so this is a translation by 2. You take everything on this axis, move it down by 2. And so, things on this axis move by 2. Things far off this axis move by their distance from the axis times 2 plus 2. And yeah, this kind of gives you an algorithm for finding axes, which is take a random point, map it to something else, and go along that path between where it gets mapped. And then that'll give you something that moves shorter distance, unless it moves the same distance, in which case you're on a characteristic set of the isometry. Okay. And then let's see how this same matrix acts on the two-adic tree. Well, yeah, according to the algorithm, we're going to multiply our Q by 9, but then we want to reduce it. And so, for example, if we have n is 3, so we have 8, 1, 0, 1, and we multiply 1 by 9, we'll get 8, 9, 0, 1, subtract 8, and you get it back. So this element is fixed, whereas this is not, because 1 and 9 aren't equivalent mod 16. And so what ends up happening is you fix this axis and you fix a neighborhood of the axis. And then beyond that, you're going to swap these two things. And so, I mean, that says that when you square it, this will be fixed. And you can actually prove that when you square it, that's fixed, and then the next layer shuffles by p cycle. Okay, let's look at another matrix. Okay, I'll call this B. It's 1/8, 9, 1/32, 41/4. Okay, and yeah, so this acting on the three-adic tree. I won't really describe this computation too much, but it's going to fix the matrix 3, 0, 0, 1, and it's going to fix a neighborhood of this. And then it's going to do a 3 cycle here. And kind of as I was describing before, its cube is going to do a 3 cycle. Well, sorry, its cube is going to fix the 2 neighborhood of that vertex and then do a 3 cycle on each of these little pieces. And yeah, I mean, you just prove that with the binomial theorem, really, applied to, well, it's going to be the identity. So it's conjugate into PSL2 ZP, reduce mod PZP. If you're the identity there, then you're of the form I plus P times some other matrix. Taking a pth power of that, you can see the way that pushes things out while keeping the shuffling as P cycles. Okay, and then let's see how the same matrix acts on the two-adic tree. Well, yeah, the characteristic polynomial is equivalent to x squared minus 1 mod 8. And we get these fixed points on the boundary. And so since these are fixed on the boundary, and, well, yeah, what do I want to say? Yeah, this allows you to find kind of the axis it's translating along. So since the trace of this matrix has denominator, positive power of 2. This implies that it's going to be a translation on this. And yeah, you can even find the endpoints of this axis according to that. All right, so this kind of leads us to this classification of these elements. So, I mean, for any tree isometry, you're either going to be hyperbolic and have an axis, or you're going to be elliptic. But kind of as we've seen, there's kind of a further refinement of these elliptic elements. And I came up with some silly names for them. Okay, so hyperbolic has an axis. And then we have these loxodromish elliptics, which fix an axis and then do these shuffling. So, oops. Yeah, this one was an example. So it has this big fixed axis and then does some shuffling. We got these parabolic elliptics. Yeah, I mean, if you have a parabolic isometry, like 1x0, 1 in these trees. So like a unipotent, for example. We're looking at PSL at the moment. Yeah, you're going to have one fixed point on the boundary and then fix kind of like a horoball around that almost, and then do some shuffling down. And then there's these strongly elliptic, which fix a point in the tree and 0 points in the boundary. And so these are going to have a compact fixed set. Yeah, and so the way to determine what kind of elliptic you are is just determined by the action on the boundary. And so the trace determines the discriminant, which can either be a non-zero square, 0, or a non. And those are these 3 cases respectively. Okay. Yeah, so let me describe a little bit the ways we can kind of look at all these trees at once. So yeah, it's often convenient to study all the p-adic trees at once. So we can build a space called A, the Adels, in which Q is a discrete and co-compact subgroup, much like the relationship between R and Z, right? So yeah. And yeah, there's a really beautiful topological way to think about this. So let's start with R mod Z, the circle. And basically, we're just going to look at the space of finite covers of this. And so if you have prime degree, you're going to be right above it. And then if you have maybe degree, say 6, well, you can factor that map here through either of these. And yeah, so taking this inverse limit here, you obtain the profinite completion kind of thing. And yeah, really this space A mod Q, let's discuss what it looks like. So this is going to fiber over the circle with fiber a Cantor set. And so this is Z hat, the profinite integers, with monodromy x goes to x plus 1. Since Z hat is a completion of Z and Z is dense in Z hat, there's kind of a base leaf R in A mod Q that starts at 0 plus Q, and then goes along with R, and it's going to spin around this thing, and it's going to hit everything in Z. And since Z is dense in Z hat, that leaf itself is dense. Okay, and so the Adels allow us to collect all the completions of Q into a single well-behaved object. And if we have an algebraic group defined over Q, we can talk about its adelic points, which is going to be a lattice in the appropriate sense. Okay, so some kind of example consequences. If we have a number field K and a finitely generated group with a faithful representation into PSL2K, and it's pre-compact for every infinite place V. So at every real and complex embedding, you're in, an orthogonal or unitary group, then gamma is going to act properly on a finite product of locally finite trees. If K has a real embedding, then gamma is embedding in SO2, and so it's going to be abelian. So this is more interesting when K is totally imaginary. And so, okay, here's a question. Is this a faithful representation of this group? And yes, I won't fully go into my interest in this question, but yeah, this is fairly simple representation I found, and I think it's the simplest of this group with the relevant properties. The next one I can find is way bigger. Okay, and then I'll mention some fact that these generalized Ramanujan conjectures imply that this adelic flow on this space is exponentially mixing. I'll leave that just out there for a moment. Okay, now I want to talk about these rational quaternions. So this is this set of a plus bi plus cj plus dk, where ij and k do their usual things. These are not all zero, and we're going to look it up to the action of q star. So each rational quaternion has unique minimal integral representative, right? So clear denominators and then pull out any prime factors that occur in all a, b, c, d. Jacobi theorem on the number of integer solutions. To this, we can actually deduce that for a fixed prime p, the rational quaternions whose integer representation, that have an integer representation with norm a power of p, right? This forms a lattice in PGL2QP, and so it's a finally generated lattice in a tree, and so it's a finally generated free group. And we can tell the rank by, it's going to be p plus 1 over 2. That's if it's transitive on the vertices, which it is. And then we can deduce the stronger conclusion that this is a lattice in H sub A, which really is the general linear group over the finite adels. And so HQ has a nice action on this associated building, which is a locally compact subset of an infinite product of trees. Okay, I just have like one more minute. What? I guess, yeah, this just gives us a bunch of examples of ways to take just the theorem of number theory and then turn it into an interesting statement about one of these groups acting on these trees. I think I'll end it there. Thank you very much for your attention. And yeah.
Well, thanks, Nick. So any questions for Nick?
I have a question, if I may.
Yeah.
Thanks for your presentation, Nick. My name's Stefan. You mentioned you've done some computations in Mathematica for the, the original action PGL2QP acting on the tree. Can you tell me a little bit more about that? What sort of computations you've done? What's the input? What's the output?
Yeah. So I mean, I guess sort of the input is, well, okay. So kind of the secret lurking beneath this, and why I mentioned some of these things is I'm interested in finding surface subgroups of, say, this group, for example. And so the various explicit things I gave were representations of surface groups into, and so, yeah, I mean, so like kind of the simple, the first thing that these coordinates are useful for is, the input is a rational matrix plus a vertex of this form, and the output is another vertex put into this form.
The image vertex.
Yeah, and then so some like kind of related little routine subroutines you can get are like the translation distance, the size of the fixed set.
Yeah, right.
Yeah, these.
That's really good. So I've developed a package for groups acting on trees in GAP, if you're familiar with that, the theoretic programming language, and that's together with some students here in Newcastle. And the student who looked into this specific action here, PGL2QP, I think he has done something very similar to what you've done.
Gotcha.
In GAP. So it would be good to compare that in detail and see if we can transfer that across. And
yeah, sounds good.
Yeah, I'll follow up on that with you. Thanks.
Yeah.
To add to that, my student Ari has also done something very similar. So yeah, we should definitely talk about that.
Okay.
What did your student use, Jeroen? What language?
I don't know, but he's here. He can tell us.
Hi, can you hear me?
Yes.
Yeah, well, what I did was write do a visualizer for isometries, the Broughton tree. Yeah, I was, well, I used TypeScript actually because I wanted it to be like interactive. So I put it on the web rather than using an actual like graphics package.
Very good.
Yeah.
So is it on the web?
Yeah. I can like post a link to it actually if you're interested.
Yeah. Why don't we post a link in the chat?
Sounds good.
Yeah.
Oh, very good. Okay, I think we should start an email thread, Nick, Ari, and Jeroen, to compare all of this.
All right. So any other questions?
How do I send a?
You should be able to just post in the chat.
Oh yeah, I found it.
Yeah. Thanks. Any other questions? Okay, if no, I think let's thank the speaker again. Now stop the recording.